what I'm going to call I want to talk about this idea of what's called a proof progression. And it kind of starts at where we're going to be at today with this angle stuff that we're going to look at. And it starts with the idea of, I know over the course of the past however many years, that students just have a hell of a time looking at a proof and knowing where they want to start, to be honest with you. They look at information that might look like, give me 1 second here. They might look at something like this and just be completely, totally overwhelmed. Given BC is perpendicular AD, BC is the angle bisector of angle C, prove that triangle ABC is BBC. And what happens here a lot of times, you're welcome, is that students get completely and totally overwhelmed by what's called a given statement. And what I've tried to do over the past few years, especially I'd say past 4 or 5 years of geometry since I've been in this building, is that I've tried my best to take away that anxiety level when it comes to the proof, because Lord knows you guys will have it. Everybody does. If you don't, awesome. But more often than not, someone's going to look at it and go, and you climb up and you go, I don't know where to start. Well, what I've kind of developed here is this kind of like a visual organizer, a graphic organizer, if you will, in a way that keeps all of your how-tos, if you will, on one sheet of paper. And it's kind of like how we have that reason bank, but this winds up being more of a proof bank, if you will. Okay? You put away your phone. Great, thanks. So what I want to do is show you guys what I mean. I want to define a couple of what I call progressions on this sheet. Don't lose this. And as we get going and working with progression stuff, one of the things I tell students to do at the end of a class period after we've done like a whole principle is that I usually tell them, make sure you take a picture of it, because if you do lose a piece of paper, I know you're not going to lose your phone. So that way you have like a backup. It's like doing a backup copy. All right? So you'll notice on this sheet of paper coming around that there are, 24 squares? Front and back, there's about 24. Thank you, ma'am. Yes, ma'am. Yes, sir. You need a couple. No problem. I figured we'd be short somewhere. I felt like one in the last time. Right. Now, what I mean by this stuff, what I mean by these things is a lot of times when we're in class, when we get to like a specific definition or an if-then statement, if you will, you're going to see me do this on the board. If you see me draw a box, that generally means, hey, bozo, take out your progression sheet and put it in the box. Yes, ma'am. Oh, I thought you had a question. Never mind. I didn't want to help you. All right. So one of the easiest things to kind of show you guys why I use this and how it fills itself out is to walk you guys through with what I think is one of the easiest progressions. And what I mean by that is when you're given a definition, what can you say with it? Okay. Now, we all know what a midpoint does, right? What's a midpoint do? Cuts a segment in half. Let's create it then. What do you know about those segments? They're the same, but we say that in geometry we say then that they are congruent. Very good. Okay. So don't write this down yet. I want to show you what it would look like as I'm going through this. Yeah, I was looking through you up there. You went that way. For example, if given a midpoint. Now, what I mean by that is, as we go along into actual triangle proofs or segment proofs or angle proofs, which we'll talk about more tomorrow. Yes, sir. I would wait a second before I fill this in. We'll have a time here at the end, in a minute or two, to fill it all in, and we'll re-walk through the whole thing. If you're ever given a midpoint, we know what a midpoint does. It cuts a segment into two equal congruent segments. So if you have a midpoint, then somewhere you're going to have some segment congruent to some other segment. In as generic terms as possible, does that change it? Do letters or anything here have any bearing upon the problem? You can have any set of letters, because if you know that A is the midpoint of xy, then AX and SA and AY would have to be the same. And C is the midpoint of DI. DC, CF. It's the idea is that you guys know how to put the lettering together because we've learned how to do that. Bless you. It's the idea that you get, when you know that something exists, what can you say about it? And that's usually the biggest hurdle that students have when it comes to the idea of looking at something like, oh, God, whoa, huh? And that's what's helpful with this progression sheet. It takes away that. Okay. So here's what it would do. I would put something like this, and this is, if you guys wanted to start this now, right in there, and you're in the first square, or any square, it doesn't matter which one. I would put in there, if given midpoint, then segment convert to segment. Now, don't just use up the entire square, because what I'm going to do here in a second is show an example of what it would look like in words and what it's going to look like in that two column. For example, X is midpoint of AB. You're given X is a midpoint of AB. Well, X is a midpoint of AB. What would that look like? What's the main segment to start with? AB, right? So it would look like this. Here's A, here's B. Where's X? In the middle, okay? According to that diagram then, what two segments would have to be congruent? Very good. And what would you do to that diagram? No, what would you do to it to show that they're equal? The marks to it, very good, yeah. Put that little tick mark, okay? So in my mind, I don't know what the picture looks like, nor do I really care what the picture looks like, but I know that I can make my own picture. I can make my own diagram because I know what the definition means. You okay with that? All right, now in terms of what I would do in my statements and reasons. Given X is midpoint of AB. Well, since X is a midpoint of AB, we know then that you have two congruent segments because it says so. If given a midpoint, then segment congruent segment. Well, what are the segments that are congruent according to your own little example you used? What letters? All right, AX is congruent to XB. And this is the big thing that people tend to forget about. The reason that we can use that, the reason that we can write that down is because we just used the definition of a what? Of what? What are we talking about here? What is this a definition of? Well, just by going from here you have this, then this. What's that the definition of using? Midpoint. It's just the definition of a midpoint. If you're given a midpoint, you're going to use the definition of a midpoint. If you're given an angle bisector, you're going to use the definition of an angle bisector. Yes, ma'am. About the right one. I would write definition midpoint. And this is that's kind of the tie-in to a lot of proofs. When you're given something, you use that something's definition. You have an angle bisector, then your definition of angle bisector. If you've got perpendicular, you've got definition of perpendicular, and so on and so on. But you had your kid. Does that make sense, though?
Yeah.
So as we go through these ideas of what's called progressions, we'll have midpoints, angle bisectors, perpendicular, right angles, vertical angles, linear, supplementary, complementary, and so on and so on and so on and so on. And that's what stinks about geometry is that there's so many stinking definitions that if you don't know where to start as far as your terminology is concerned, the rest of it sucks. This puts it on paper, and you can go back and you can reference this and say, all right, I have a midpoint, I'm looking at this. Oh, midpoint tells me segment congruent to segment, and that's what it should look like. Okay? Yeah, perfect. Okay. That's exactly what a progression does. It's there to take the nightmare of this into smaller chunks, because if you know you have perpendicular, then you know you have right angles. If you know you have right angles, you know that they're congruent. It's a whole sequence of events. It's basically a transitive property over and over and over and over. Oh, transitive property is the law of syllogism. You didn't know that. Okay. Not bad so far? All right, let's look at another one real quick that's super easy to talk about. I don't want to draw these, I can just do this. If given angle bisector, if I'm given an angle, what is an angle bisector? Very good. What's created? Right. Exactly. Very good. Very good. Again, by definition, we know that an angle bisector, excuse me, an angle bisector bisects an angle, which therefore creates two congruent angles. So a second ago, we just said if I had a midpoint, then you would say segment congruent to segment. Now I'm going to say if given angle bisector, then angle congruent angle. Good. You all right? All right. Yes. Yes. Because what's going to happen eventually is it will be, if you know that you have a midpoint, then you know you have congruent segments, and then we're going to start to build into other parts. Because eventually we'll be able to look at a pair of triangles. If I look at that and I know I have a midpoint, and I know I have right angles, and then I know that this is a shared side, then I know that this triangle are the same because of what we call side angle side. It's the idea that you can know where to start to get to it, and midpoint is an easy place to start. We'll get there. We're not doing this like for another month, but we'll get there. All right. All this stuff is baby steps to get to that point. Okay, they really are. They're just baby steps to get to here. And this progression sheet doesn't go away. We just keep adding to it. That's why I say don't lose it. Okay. So example.
What if we use on the boxes?
I don't think you will. I think we use about 16 or so of them, maybe. And that's at the most. Some of them I just put a couple extra ones in there just to have for some other definitions later on. But I don't think. I think that having the 24 squares is the perfect size because the boxes are nice and big, and we don't have to worry about it. We have. I don't think I've ever come across where we needed more than that. Then we're really screwed. Yeah, right. All right. Example. Let's say that BX is the angle bisector of angle A, B, C. So if I say that BX is the angle bisector of angle ABC, what do you think the first thing I should do is? According to my progression sheet. Well, What should I put on there? Mhm. Sorry, I had to write that smaller so I could fit it in here. Is that all right? Yeah, a lot of times I try to write neatly, and apparently I didn't go to school that day. They taught me penmanship. I'm finding out that our oldest son is kind of like that too. His handwriting is so now, like we were just saying, draw the example. So we draw our little picture. A, B, C, there's X. Now we know that an angle bisector cuts an angle into two congruent equal parts. This angle bisector created what two angles being congruent? Everybody hear that okay? The two angles that were formed would have been ABX and XBC. So in my quick little generic diagram, I would do that. And then now knowing what all of that does, putting it together, I would put it in my two-column proof. And I would use that as my example. BX is the angle bisector of angle ABC. That's given. Which therefore means, since according to my little generic diagram that we just drew, I can then say that angles ABX is congruent to angle of XBC. And my reason here is going to be because we use the definition of an. So your reason is the definition of angle bisector. Right. A lot of, remember, our reason banks, our reasons, your statements, what you're doing, why. And these are definitions, theorems, postulates, so on and so on. Yes, ma'am. Okay. So it just looks weird, but in about a couple of weeks when we get into the actual, well, actually, sorry, rephrase that. Tomorrow we'll actually do our first real segment and our real angle proofs. But I just wanted to start with something very, very straightforward with you guys on why we write these out in such a very specific language. Just like yesterday and the day before, we were writing out our reasons, your properties, your addition property, subtraction property, all those, why they were such very specific terms. Because here you have to be. Because if you don't, then it's invalid. Is it not so bad? I mean, I know you guys have all heard about the proofs that they're just, people have always said, oh, it's so bad. But I try my best to not to make it happen. Right? I mean, I shouldn't say make it happen, make you feel that scared. I mean, I can say, whoa! I really want to scare you. I thought smack me, so I didn't. It would have been really funny. And then I thought for a minute, where we don't do that, and I listen to my brain. You know, it's like the angel and the devil, the angel one. Squirrel. Last little bit of today's stuff then. Today's stuff we're going to talk about, along with these, is that these are all things that you have seen. What's happening today, we're going to go back to chapter 1, we worked with angle pair relationships. When we had angle pair relationships, remember we had complementary, supplementary, linear pair, and what was the last one? Vertical angles, very good. So we had those 4 angle pair relationships. What did you know about all vertical angles? They're vertical. They were what though? They're all angles, very good. They're vertical and they're angles. You guys listen very clearly. Now, what's the relationship between 1 and 3? Yes, they're equal. Why? They're because they're vertical. Just wait for me to say that. Yeah. Vertical angles, as you guys remember, vertical angles are congruent. We'll put that together as a progression later on when it comes up again. What happens with vertical angles is it's a long-winded definition. Vertical angles are congruent because they're the same angle, because as you go through it, if you think about, angles are made up of sides, 2 sides that meet the same vertex. When angles are vertical, they don't share the same sides, but they have the same vertex. But what happens is that the sides that are opposite with each other create lines. Okay. So these 2 create a line because they're opposite one another. These 2 create a line because they're opposite of one another. That's where that comes up. That's why those 2 angles. Excuse me. We know that one. What do you know about right angles? 90 degrees. Okay. So if I say that angle A is a right angle, and angle B is a right angle, what can you tell me about it? Add the other equals 180. Very good. But what else could you tell me? They're equal. In math, when things are equal, or I'm sorry, in geometry, when things are equal, they are congruent. So therefore, if we just do a little bit of, well, I don't know, logic. I know, it's a lot. What can you then tell me about all right angles? Which means all right angles are. We know that no matter what, if you have a 90-degree angle, it's a right angle, correct? And no matter what, the definition of a right angle means that it measures how many degrees? 90. And when things have equal measurement, we always know for dead certainty that there will always be. That's why they do that. We can't say that about, we can't really say that about anything else because, you know, we can say all straight angles are congruent, but they don't really help us very much. Right? But we know that all right angles are congruent. And that's another thing that we'll talk about later on when we get into another progression, one that looks like a perpendicular. Okay? We'll talk about that, I think, next week. That one comes up next week. Okay. Again, not so scary bad, is it? Okay. All right. What makes a linear pair more specific than supplementary? Do you remember? You gotta flip. You gotta flip. Remember, linear pair means they have to be together. Supplementary just means they add to equal. Right. Because what's in the word linear? Line. So a linear pair is the more specific version of supplementary because the 2 angles will always make a line. The 2 angles will always add up to equal 180 degrees, but when they're supplementary, they don't have to necessarily be next to each other. They can be in different parts. Linear pair is just a fancier version of a supplementary angle. Hence the word line. But we kind of remember that, right? You know what? I think that's enough. Okay, you're welcome. Let me give you the ones I had. So, Now I do want to show you guys one thing. Numbers 26 through 29, I didn't really talk about any of that before. And it's a lot of angle A is twice the measure of its complement. What are the angles? You're looking at So 26 reads, angle A is twice as large as its complement, angle B. All right, what do complementary angles have to equal? 90. So if I say angle A plus angle A plus angle B have to equal 90 because they're complementary, and then it says angle A is. What does the word is mean in math? Equals. Good. Angle A is twice the measure of its complement. Well, B has to be its complement, right? All right. That's is the question. She goes right to her phone and trying to have fun with it. So that means then I can do what? You guys remember how to work with linear systems of equations? Yeah. That means you can do this. What's 2b plus b? 3b. What's b have to equal? 30. So angle B is 30, which makes angle A how much?
60.
Is angle A twice the measure of angle B?
Yes.
Okay. Give these a shot. I just did one of them. The other three that are similar to that follow kind of the same pattern, just different numbers. Okay. We'll go over that tomorrow. We'll do a couple of in-class assignment briefings. And quite honestly, I don't foresee us having more than maybe one fill-in-the-blank group for homework. So it shouldn't be so bad tomorrow either. Okay? Questions? You got a couple minutes to work on? What's up?
What's the page?
124.
Okay.
It's all new.